Thank you, Faria, for the opportunity of presenting our results today. And good morning, everyone, online and in person. So today I'm going to talk about catalyst design in the context of the Eco2Fuel project, the UPV. UPV partner is the Institute of Chemical Technology in Valencia, Spain, and that we are a joint research institute between the Polytechnic University of Valencia and the Spanish National Research Council. Within the Eco2Fuel project, our main contribution was in work package 3, where we have been involved in electrocatalyst synthesis, physicochemical characterization, electrochemical screening of both anodic and cathodic materials. During the project, we have developed and evaluated a broad catalyst portfolio, but in this presentation today, I will focus on 2 representative case studies. First of all, the anode catalyst for the oxygen evolution reaction. This is a system that was not ultimately selected as the final Eco2Fuel system anode, but it served as an important benchmark and a learning platform. And actually, our results were published. This is the reference in collaboration with CNR, with Antonino and Sabrina. And the second example is the cathode catalyst for the CO2 reduction reaction. This was actually the final cathode implemented in the Eco2Fuel system, represents a direct contribution to the final technology. So I will move now to the first case study, to the anode catalyst. Nickel-iron layered double hydroxide structures are widely regarded as a benchmark for oxygen evolution reaction in alkaline media. This is mainly because since they have a 2-dimensional layered structure, this provides a high density of active sites and a tunable composition. A key aspect is the synergy between nickel and iron centers, which is known to enhance the reaction kinetics and reduce overpotentials. In addition, an important point is that these nickel-iron LDH are composed of earth-abundant elements, and this is making them particularly attractive for scalable and sustainable electrolysis technologies. For these reasons, we choose this type of materials to explore within the project. In this case, we developed a solvent-free mechanochemical synthesis for nickel-iron LDH. In this approach, the catalyst is obtained simply by mechanical grinding of the solid precursors during 1 hour at room temperature. We don't use any solvents or any external heating. An important advantage of this route is the significant reduction of cost and environmental impact, since we eliminate solvent, minimize energy inputs, and we reduce washing consumption during the final washing steps. And actually, we obtain the same structure as the catalyst obtained by traditional aqueous phase methods. For example, here you can see some characterization by X-ray diffraction and by microscopy. Basically, in the X-ray diffraction pattern, we see the characteristic features corresponding to nickel-based LDH structure. One important point is that the peaks are very broad, and this is already indicating some degree of low crystallinity. This is due to the solvent-free synthetic method. Here, the SEM images show that the material is composed by an agglomeration of sheet-like particles, which are typical morphology of LDH systems. We can observe also that the size of the agglomerate is around 200 nanometers. Here in the bottom, the TM image shows that the particles are composed by the aggregation of nanosheets in the range of tens of nanometers. And here on the right, the high-resolution TM image shows the typical spacing for LDH structures that can be assigned to some of the crystallographic planes that were already observed in the X-ray diffraction pattern. Other characterization that we did was XPS. By XPS, we basically confirmed the presence of all the elements in the samples, but also we can confirm the oxidation state of nickel, which was assigned to nickel 2+, iron 3+. And here in the bottom right, we have the spectral of oxygen, where we observe basically the main peak of the hydroxide, and then to small contributions for oxide and absorbed water. The performance of this nickel iron LDH catalyst was evaluated under a single cell membrane electrode assembly. This was performed in collaboration with CNR, with Antonino and Sabrina. These are the conditions were used during this experiments, and I'm going to jump ahead to the results. So first of all, here we can see the polarization curve. We observe that our nickel iron LDH catalyst reaches 10 milliamps per square centimeter at an overpotential of 220 millivolts, which already indicates a very good activity for the oxygen evolution reaction. The corresponding Tafel slope, which is close to 100 millivolts per decade, suggests a reasonably fast reaction kinetics. This performance is well in line with what we typically expect or what is typically reported for nickel iron-based oxygen evolution catalyst, especially considering the simplicity and the sustainability of the solvent-free synthetic method. Now, regarding the stability or the durability of the catalyst, we operated the cell at a constant current density of 0.1 amps per square centimeter during 35 hours. And as you can see, the cell voltage remains stable around 1.5 volts. This indicates a good operational stability under sustained oxygen evolution conditions. Now, here in the bottom right, we have some impedance spectroscopy, electrochemical impedance spectroscopy data. So basically, here what we can see is that the nickel iron LDH catalyst reaches operation voltages between 1.8 and 2 volts. We can see here in red and blue that the semicircle becomes much smaller, showing a clear reduction in the polarization and the low frequency resistance. So that means that the oxygen evolution reaction becomes much more efficient at these voltages. So as a conclusion from this example of this anode catalyst, we demonstrate that nickel iron LDH synthesized by a solvent-free mechanochemical method shows a strong oxygen evolution performance when tested under a single cell MEA conditions. Although this catalyst was not selected as the final anode for the CO₂ fuel system, it was a robust benchmark system and providing valuable insight that supported system-level optimization. So now I will move to the cathode side. This second example, it is actually the final cathode implemented in the CO₂ fuel system and represents a direct contribution to the final technology. As Antonino mentioned earlier in his presentation, copper-based materials are recognized as benchmark cathodes for the electrochemical reduction of CO₂ because they enable the formation of multi-carbon products. Particularly, copper oxides are widely used as reference systems due to their surface composition. The oxidation states can be tuned, and they are easily implemented in device-level systems. In this project, we synthesize a copper oxide catalyst in an aqueous media under argon using simple inorganic precursor salts. The formation of the copper oxide material was monitored by a clear color change of the suspension, and the final material was obtained with very high yields. This process relies on mild conditions. We didn't use any harmful chemicals, and it was easily scalable. Regarding the material characterization, again, we use microscopy and XRD. By the XRD pattern, we can confirm that the bulk of the material is primarily composed by copper-1 oxide, a cuprite. We didn't detect any other peaks by XRD. The microscopy image show that the material is composed of homogeneously distributed particles and with a size between 100 and 200 nanometers. Now, we also use to characterize this material XPS, and basically here we use this because to characterize the surface of the material. First of all, in the carbon spectra, what we can see is a main peak that corresponds to adventitious carbon and an additional peak that corresponds to carbonate. So just to mention that here we are comparing in green our synthesized samples, in black a commercial copper oxide material for comparison, and then we have a series of upscaled samples that was done in monolithos, and this is just to show that we use this technique to compare between different samples of the same material synthesized different partners and at different scales from milligrams to multigram. So basically, the conclusions here are that the samples have the same signature, but regarding the carbonate, we have some carbonate species on the surface, and that the intensity differs depending on the synthetic conditions. Now, regarding the copper signature, all the samples show a peak here around 934 electron volts, together with a satellite peak. This is characteristic of the presence of copper-2 species in the surface. The commercial sample, however, show a main peak that is shifted, and that this indicates the presence of mainly copper-1 in the sample. So after the characterization, I want to share some electrocatalytic performance that was done here at UPV using a flow cell system. This is a commercial flow cell. And I put here all the conditions, and just to mention that the results I'm going to show are the results obtained with this configuration, and they vary drastically depending on what system we use. For example, what Antonino was showing earlier, it's a completely different system, but I wanted to share these results with you today. So these are the electrochemical results of the catalyst using these flow cell conditions, using a chronoamperometry from 1 to 2.5 amps. On the left, we show the performance of the commercial reference catalyst, and on the right we show the performance of our copper oxide catalyst. So the bar charts are the Faraday efficiency, and we can see that as the current increases, both catalysts produce mainly liquid products. And in our case, with these conditions and with this flow cell system, we obtain ethanol as the dominant product. Now, this slide focuses mainly on the C2 plus products. In both cases, the Faraday efficiency for C2 plus products increases, again, with increasing the current. And importantly, our copper oxide sample shows comparable or even higher C2 plus selectivity at the highest current density compared to the commercial sample. So this demonstrates that this material performs very well under practical flow cell conditions, and it was this material was scaled up by monolithos. I think they will present after me, and then it was also tested in other more relevant electrochemical conditions for the CO₂ fuel system. So as conclusions for the cathode, copper oxide cathodes confirm their role as a benchmark materials for the CO₂ electrode reduction. Our synthesized copper oxide shows phase purity, homogeneous morphology, comparable surface composition to the upscale and the commercial samples. When we tested in a commercial flow cell, we observed stable operation at high current, product distribution similar to the commercial copper oxide reference, and the efficient formation of C2 plus products that increase when we increase the current density. So just to close my presentation, we have contributed to the World Package 3 catalyst development in the CO₂ fuel project. In the case of the anode, the example I showed is a benchmark system that provides key insights for membrane electrode assembly operation. In the cathode case, we have designed the synthesis of a scalable copper oxide catalyst that shows competitive CO₂ reduction performance. And yeah, these results support CO₂ fuel electrochemical CO₂ conversion strategy. I want to thank you all for your attention. This is our group here in Valencia, and I want to thank also CO₂ fuel and Faria for the opportunity of presenting today. And we'll be happy to answer any questions.
I see there is a question on in the chat. Very interesting work. In general, is there a scope for an alternative anode reaction? Yeah, an anode reaction that can be commercialized?
Oh, wow. You mean other reaction than, I understand that they mean other reaction than oxygen evolution, right?
Yeah.
Yeah, I assume all the anode reactions.
I assume. Yeah. I mean, within the CO₂ fuel project, we have not considered any, we are focusing on the oxygen evolution reaction. But I understand that there is a lot of research going on in alternative reactions. For example, it comes to my mind right now because we have, they're also working in a collaboration for the glycerol oxidation. So glycerol comes from the, as a byproduct or a waste from the biodiesel industry. And glycerol can be oxidized to produce formate. So yeah, of course, there are many other, especially organic oxidations. Yeah.
Thank you, Sara. We are running a little bit out of time, so we needed to pass it to the next presentation. Thank you once again.